I'm Katrina Kovac, and my project was on the Arbelos. So, Arbelos is a term that means a cobbler's knife, but in geometry, it is a figure, shown here, with three semicircles, one large semicircle and two smaller inscribed semicircles, which all have a diameter that share the same line, which in this case is the green line AB. Line segment, at least. So each of the semicircles is tangent to the other two semicircles. So this one is tangent to the other one, to the other inscribed and the outer. The outer is tangent to both the inscribed, and the same for the left inscribed is the same for the right inscribed. That they're both tangent to each other and the outside. So Archimedes became fascinated with the cobbler's knife. So first he generalized the shape by making the inscribed circles different sizes. So you would see it in various arrangements, but we'll leave it over here for now. So then he decided to try and figure out the area of this region, the region within the outer circle not taken up by the two inner semicircles. So one way you can do this, that you could do this, is to take the area of the outer semicircle and subtract from it the area of the inner two semicircles. So if we were given a diameter of 4 for this semicircle and 2 for this semicircle, that would mean that the outer is 6. So for area of a circle, it is pi r squared. So area of a semicircle is pi r squared divided by 2. And for our purposes, we will name the semicircles A, B, and C. We want the area of A minus the area of B plus C. So the area of A is equal to pi. The radius is half of 6, which is 3 squared. So divided by 2. So we get 9 pi over 2, which is equal to 4.5 pi. Next, we look at the area of B, and we get pi times 2, which is half of 4, squared over 2, which is 4 pi over 2, which is just equal to 2 pi. Next, we look at the area of semicircle C, and we get that it is pi times the half of 2 is 1, so the radius is 1 squared over 2, which just comes out 2.5 pi. So that is the area of our three semicircles. So we do the area of the large one, 4.5 pi, minus these two combined, which is 2.5 pi, and we are left with 2 pi as the area for this region, which is the Arbelos. The next way he found out to do this was to construct a line that was perpendicular to the baseline, which I will make green again, and also tangent to both of the inscribed semicircles. So after you do that, if you construct a circle with the diameter of this line, the area of said circle is equal to the area of the Arbelos, no matter what the configuration is for the inscribed circles. That circle will always be the inscribed semicircles. That area of the full circle inscribed will be the area of the Arbelos. So if we had a radius of 4 for this circle, the area of the circle would be 16 pi, and so would the area of the Arbelos. So finally, he stated that also constructed along the perpendicular line that is tangent to the two semicircles, that if you construct a circle on either side that of the line that is tangent to the line and to each the outer circle and the inscribed semicircle on its half, that both the circles would be congruent to each other. And the proof for this states they constructed the line CD to extend from the semicircle, the outer semicircle. And then it states that the circle inscribed intersects with line CD at point E. And then you draw the diameter of the circle, which happens to be HE, so that E is the intersection of the circle and line CD. It is also perpendicular to the line CD, which means that it is parallel to line AB, as stated down here. And then since angle AFB and angle ACD are both right angles, line segment AE is parallel to line segment BD. Therefore, AE is perpendicular to BI. So since angle G and angle I are both right angles, we can conclude that CH, since it is right angle when it's perpendicular to AI, is parallel to line BD, since it is also perpendicular to line AI. And then we see that the ratio of AB to CD are equal to the ratio of AD to DH, which is equal to the ratio of AC to HE. And then because of this, we can then cross multiply and figure out that AC times CB is equal to AB times HE. So in like manner, if D is the diameter of the other circle, we can prove that AC times CB is equal to AB times D. Therefore, we see that D is equal to HE. So then the diameter of the circles are both equal, so then therefore the circles themselves must be equal and congruent. And that pretty much sums up my presentation of the Arbelos.